Let's begin by talking about the notion of quantum advantage. Now, as we all know, quantum computers seem to be more powerful than classical computers. Perhaps the most famous example of this apparent advantage is given by the factoring problem, where by Peter Shor's landmark result, a quantum computer can factor an integer in polynomial time, whereas there's certainly no known classical polynomial time factoring algorithm. However, while it is the case that for certain very special problems, like factoring, and in certain settings, like time complexity, we do have this apparent superpolynomial quantum advantage, it's certainly not the case that quantum computers are some sort of super machines that outperform classical computers by some gigantic margin on all problems. Instead, the more accurate statement is that quantum computers seem to be more powerful than classical computers sometimes. For example, consider the query complexity of a total function. Here, it's been proven that quantum has the most polynomial advantage over classical. And so this is a setting in which strong limitations on quantum advantage are known. In this paper, we study the quantum advantage question in the small space setting, and we prove tight limitations on the degree to which quantum can outperform classical. In particular, we give the first example of a language that can be recognized by a classical algorithm in log space and polytime, but for which no quantum algorithm can do any better. That is, any quantum algorithm that recognizes this language in polytime needs log space. And so this is a setting in which provably there is no quantum advantage. Our second example pertains to the finite automata world. Here, we give the first example of a language that can't be recognized by any sort of classical two-way finite automaton in any time bound, but can be recognized by a quantum two-way finite automaton in exponential time, and for which exponential time is provably needed. And so this second example gives a setting in which quantum advantage exists, but strong limitations on quantum advantage can now be given. Far more generally, we give a new technique that can be used to lower bound the quantum time-space complexity of any language. And the above-mentioned results are just special cases of this far more general technique. But before delving into the details of these results, let me first spend a minute trying to convince you that space actually matters in quantum computation. Now, the existence of this apparent quantum advantage for certain important problems, like factoring, has provided excellent motivation for constructing real, physical experimental quantum computers. And after several decades of progress, we've entered what John Preskill calls the noisy intermediate scale era of quantum computation, where here intermediate scale refers to the fact that these quantum computers have few qubits. For example, consider a state-of-the-art quantum computer, IBM's Q system, which has 53 qubits. To put that number in perspective, we can compare this state-of-the-art quantum computer with a not at all state-of-the-art classical computer, Apple's iPhone 7, which has 128 gigabytes of memory and has a retail cost of something like $400. Now, I don't know exactly how much IBM's Q system cost to build. That's just some sort of trade secret, but I think we can safely assume it's a great deal more than $400. Of course, this is a somewhat unfair comparison, because when one says the iPhone 7 has 128 gigabytes of memory, that is conflating together multiple different kinds of memory. But the basic message is true. Current and near-term quantum computers have few qubits. They have a small amount of quantum memory. And so space really is important in quantum computation. And if you believe that, then it's natural to try to understand what is the power of a quantum computer that has only a small amount of space. We first focus on the extreme case of a quantum computer that has only a constant amount of space, which we model using finite automata. In particular, we consider the two-way quantum classical finite automaton, or 2QCFA, as version defined by Ambinas and Watrous, as follows. We start with a 2DFA, that is a two-way deterministic finite automaton, and we augment it with a quantum register of constant size. We allow the machine to interact with this quantum register however it likes, performing arbitrary unitary transformations and arbitrary quantum measurements, and we allow the machine to use the results of those quantum measurements however it likes. Now, as this is a standard model, I won't spend any more time belaboring the details of the definition, but they are here on the slide, and so if you'd like to spend a moment staring at the details, feel free to pause the video at this point. Continuing, In the same paper in which Mbinus and Watrous first defined this model, they also exhibited two examples of languages for which 2QCFA provably outperform any sort of classical finite automata. The first such example was the language LEQ, which consists of a run of zeros followed by an equal length run of ones. As they showed, a 2QCFA can recognize this language in order n to the fourth time, and in a recent paper I improved that to n cubed time. Of course, one can't hope to do much better, as trivially this language can be recognized in little o(n) time. Now, as a 2QCFA is just a 2DFA plus a quantum register, it's natural to compare 2QCFA with 2DFA, where it's known that 2DFA cannot recognize this language in any time bound. However, to be completely fair, we should also compare 2QCFA with 2PFA, two-way probabilistic finite automata, which are simply 2DFA that have been augmented with the ability to flip coins, as probabilistic computation is a particular case of classical computation. 2PFA actually can recognize this language in exponential time, but there's a matching lower bound. Exponential time is provably needed. And so this language really is an example of provable quantum advantage in the constant space setting. A 2QCFA can recognize it in polynomial time, whereas a 2PFA needs exponential time. The second example, considered by Mbinus and Watrous, was the palindrome language, which they showed can be recognized by a 2QCFA in exponential time. This then gives us another example of provable quantum advantage in the constant space setting, as it's known that 2DFA and even 2PFA cannot recognize palindrome in any time bound. But what about a lower bound for 2QCFA? Can we do any better? Is there a 2QCFA that recognizes palindrome in sub-exponential time, maybe even in polynomial time, as was the case for LEQ? More generally, is there any language that can be recognized by a 2QCFA in exponential time which we can prove can't be recognized in sub-exponential time, or at least not in polynomial time? These were all open questions, which we resolve in this paper. In particular, we prove no, you can't do any better than the original Mbinus-Watrous construction. No 2QCFA can recognize palindrome in sub-exponential time, where we emphasize that this is the first example of a language that provably requires exponential time on a quantum finite automaton. Now, this result for palindrome is merely a special case of a far more general result. Namely, for any language L, we prove a lower bound on the running time of any 2QCFA that recognizes L. To be precise, we show that the running time has to go at least as fast as the non-regularity of L raised to the power of some constant b, where non-regularity is a particular hardness measure of a language, originally defined by Dwork and Stockmeyer, and this constant b just depends on the number of states of the 2QCFA. If we then consider the particular example of palindromes, then we can establish an exponential lower bound on the non-regularity of this language, which, by the above general result, then immediately implies that no 2QCFA can recognize palindrome in sub-exponential time. Now, in order to put our lower bound for 2QCFA in perspective, it's natural to compare it to the analogous result for 2PFA, proven by Dwork and Stockmeyer, who showed that the running time of any 2PFA is lower bounded by an exponential in their hardness measure, where we note that both of these lower bounds are essentially tight. That is, the Dwork-Stockmeyer lower bound for 2PFA is exponentially stronger than our lower bound for 2QCFA. However, this exponential difference can't be helped. This is merely yet another example of a setting in which quantum computers exponentially outperform classical computers, provably. Now, all of the results stated so far apply to quantum finite automata, which are just quantum computers that have only a constant amount of space. We next observe that the same technique also yields results for quantum computers that use a small amount of space. In particular, consider a quantum Turing machine that uses space S of n, which is sublogarithmic, that is little o log n space. Or if you prefer, you can consider the more standard but equivalent quantum circuit model, in which case this is just a quantum circuit on S of n qubits. Then, for any language, we prove a lower bound on the running time of any such machine that recognizes that language, where now this lower bound is expressed in terms of both the non-regularity of the language and the amount of space we allow the machine to use. In the interest of brevity, we'll just consider one example, the palindrome language, again. Here we prove that no sublogarithmic space quantum computer can recognize palindrome even if given time 2 to the n to the 1 minus epsilon. To put that lower bound in perspective, Note that even a deterministic computer can easily recognize palindrome in log space and polytime, and so a quantum computer can certainly do the same. But our lower bound says that a quantum computer can't do any better. If one wants to recognize palindrome and polytime, then log space is necessary. To provide further context for our lower bound, recall that any language that can be recognized by a quantum computer in log space can also be recognized by a deterministic computer in log squared space. Both this result and our result provide strong limitations on quantum advantage in the small space setting, but the exact details of those limitations are incomparable. Next, I want to discuss the key tool that was used to prove all of the results mentioned so far, which is a quantum analog of the classical crossing sequence argument. Now, crossing sequences are an ancient technique, defined originally by Henny in 1965, who used them to prove lower bounds against deterministic Turing machines. For example, one can show that any language that can be recognized in time o and log n must be regular. Henny's original deterministic crossing sequence technique was then generalized to probabilistic computation by Dworkin-Stockmeier and Greenberg and Weiss, which enabled them to prove their lower bounds against 2PFA that were stated earlier. I can now generalize this technique even further to quantum computation. And then, using these quantum crossing sequences, I can prove the various lower bounds against 2QCFA and small space quantum computers that were stated earlier. The remainder of this talk will be devoted to explaining this notion of crossing sequences. First, I'll briefly sketch Henny's original deterministic crossing sequence argument, and then I'll provide a high-level overview of my quantum analog. Suppose we have a deterministic Turing machine, M, and suppose we also have an input string that's been partitioned into two pieces. The left part of the string we call x, and the right part we call y. We then run M on the input xy, and we consider the path M's head takes during this computation. So in this example, the head first meanders around the x part of the string for a while, changing directions multiple times before the first time it crosses into the y part of the string. Then it moves around the y part of the string for a while, crossing back into the x part of the string. Then it moves around the x part of the string for a while, crossing back into the y part of the string, and so on. We then keep track of the state the finite control of M is in each time M's head crosses the boundary between x and y. So the first time we cross from x into y, the finite control is in state C1. Then we cross from y back into x, we're in state C2, and so on. We then define the crossing sequence of M on the partitioned input xy as this sequence of states, C1, C2, and so on, that M is in at its various crossings of the boundary. So that's the definition of a crossing sequence. Next, we will see how crossing sequences can be used to prove lower bounds. Let's now consider running M on a pair of partitioned inputs, xy and xy prime, where it's only the suffixes of these two strings that differ. Suppose that the crossing sequence of M, when it's run on the input xy, is identical to the crossing sequence of M on xy prime. Then we claim that M has to make the same decision on xy and xy prime. That is, both of these inputs have to be accepted, or both have to be rejected. Let's see why that's the case. We consider running M on xy and on xy prime. The goal will be to understand the relationship between these two computations. Let's start by thinking about the initial segment of the computation of M on the input xy, where here we pause the computation as soon as M's head crosses the boundary into the suffix y. If we then consider the analogous initial segment of the computation of M on xy prime, we immediately see that these two initial segments must be identical, simply because these two inputs share the same prefix, x. We then consider the second segment of the computation of M on the input xy, where now we pause this computation after the next boundary crossing. If we then consider the analogous second segment of the computation of M on the input xy prime, this part of the computation might look completely different, as the suffix y and the suffix y prime might be very different strings. However, by our assumption that the crossing sequences are identical, we can conclude that M is in the same state, C2, after the second crossing in both cases. Continuing this process, we then consider the third segment of the computation in each of these two cases, and we observe that these segments must be identical. This follows from the fact that at the beginning of the third segment, the relevant portion of the configuration of M is exactly the same in both cases. That is to say, the finite control of M is in the same state, C2, M's head is in the same position, one cell to the left of the boundary, and the portion of the tape to the left of the boundary has the same contents in both cases. Of course, this may no longer be the string X, as M could have overwritten part of that string during the first segment of this computation. But as those first segments were identical, the string in the left part of the tape will be identical in the two cases, and so the third segment of the computation will be identical in the two cases. Continuing, we then consider the fourth segment of the computation of M on xy, and the fourth segment of the computation of M on xy prime, which again might look completely different, but by our assumption that the crossing sequences are identical, we know that M is in the same state C4 after the fourth crossing in both cases. We then continue this process until M eventually halts on the input xy. In this example, that happens during the fifth segment, and M accepts. By the same argument as before, the corresponding segment of M's computation on xy prime must be identical, and so M must accept xy prime, as desired. The same argument proves the claim in the general case. Identical crossing sequences imply identical answers. Next, we consider a lower bound technique that makes use of this claim. Suppose we have a hard language L, and suppose that we also have a deterministic Turing machine M that recognizes L quickly, where I won't be at all specific about the hardness measure or running time bound being considered here. What we would like to do is find a bad pair of partition strings, xy and xy prime, such that M has to make a mistake on one of them, thereby contradicting the assumption that M recognizes L quickly. To accomplish this, we require one of the strings to be in the language, and then the other string to be not in the language, and we also require M to have identical crossing sequences on these two strings. If these conditions are satisfied, then by the previous claim, M must make the same decision on these two strings. But only one of them is in the language, and so M must be wrong on one of these two strings. Next, I will give an overview of my quantum version of crossing sequences. Here, we consider running a 2QCFA, M, on a partitioned input, xy. Now, of course, the basic setup here is quite similar to that of the deterministic case that we've just considered. However, the fact that we are now working with a quantum model of computation adds all sorts of new difficulties. In particular, suppose we try to mimic the definition of deterministic crossing sequences by considering the path the head takes during this computation. Then we immediately run into a problem, as quantum measurement is a probabilistic process, and so whenever a 2QCFA performs a quantum measurement, the machine probabilistically branches according to the different possible measurement outcomes. And so what we've really illustrated here is the path taken by the head in a single branch of the computation. Moreover, even if we ignore this issue for the moment and just fix our attention on one single branch of the computation, we then immediately run into a new problem. Suppose we try to keep track of M's state every time this single branch crosses the boundary between x and y. In the previous deterministic case, this only entailed keeping track of the state of the finite control of the machine. However, now, in the current 2QCFA case, we have to deal with a much more complicated notion of state, as we have to consider both the classic state of the finite control and also the current contents of the quantum register, which is described by a quantum state. And so we immediately have these two serious issues, the probabilistic computation tree and this more complicated notion of a state, which we will have to deal with in order to define a quantum analog of crossing sequences. Though other issues will also arise later in the analysis. We begin by considering the structure of a 2QCFA's probabilistic computation tree. As before, we run M on the input xy. The total configuration of M at any particular point in time and on any particular branch of the computation is described by a triple consisting of the current classic state, the current quantum state, and the current head position. Each node of the computation tree consists of a single configuration. In particular, the root of the tree is simply m's configuration at the very beginning of the computation. In order to populate the rest of the tree, we run m one step at a time. Each step of the computation involves either applying a unitary transformation to the quantum register or performing a quantum measurement, as well as also updating the classic state and moving the head one cell in either direction. The choice of which operation to perform at any given step depends only on the current classic state and the input symbol that's currently under the head. Suppose, for example, that the first step of the computation involves applying a unitary transformation. Then the initial configuration will have a single child, given by the configuration that m will be in after that transformation. Suppose that the next step of the computation involves, instead, performing a quantum measurement. Then for each possible outcome of that measurement, the current configuration will have a child, given by the configuration that m would be in, assuming that measurement outcome occurs. Now, of course, different measurement outcomes may occur with different probabilities, and so each child may be reached with a different probability. Continuing this process one step further, it may be the case that in one configuration, a quantum measurement is performed, whereas in a different configuration, a unitary transformation is performed. Next, we'll use these computation trees to define a stopping ensemble of a 2QCFA, which is a quantum analog of Dworkin Stockmeyer's notion of a stopping ensemble of a 2PFA. As before, we consider running m on the input xy, but now we only run m until it is finished computing on the prefix x, where we say that a particular branch of the computation has finished computing on x as soon as that branch crosses into the y part of the input, or accepts or rejects. To illustrate this idea, let's consider an example of a possible computation of m one step at a time. We start with the initial configuration of m, the configuration after one step, the collection of possible configurations after two steps, and then the collection of possible configurations after three steps, where in this example, the leftmost branch of the computation has accepted and so has finished computing. We then continue running the remaining branches, and after the next step, the rightmost branch of the computation has crossed from the x part of the input into the y part of the input. And so that branch has finished computing on x. We then pause that branch of the computation. In our analysis, we don't modify the behavior of the machine, and then we continue running the remaining branches. After a while, all of the branches in this example computation have finished computing on x. The stopping ensemble consists of the collection of all terminal configurations from this process, where we also keep track of the probability with which each of these configurations is reached. Now, I am glossing over certain details here. For example, a given branch might run forever without crossing, but those issues can be dealt with. We will now describe the entire computation of m on the input xy by repeatedly applying the idea from the previous slide. We begin by considering the initial configuration of m, and we define the first starting ensemble to consist of just this one single configuration. We then run m until it is finished computing on the prefix x, at which point we have our first stopping ensemble. A stopping ensemble contains accepting and rejecting configurations, which correspond to branches of the computation which are completely finished. But it also contains crossing configurations, which correspond to branches that were paused as soon as they entered y. We now want to allow those branches to resume. In order to do this, we define a second starting ensemble, which is equal to the first stopping ensemble. We then run m until it is finished computing on the suffix y, where now everything is defined symmetrically. That is, we run each branch until it accepts, rejects, or re-enters x. We then obtain our second stopping ensemble. And then we keep going. Now, in order to motivate what's coming next, notice that the process that transforms an arbitrary starting ensemble to its corresponding stopping ensemble has a very nice description. Namely, all we do is run each branch until it accepts, rejects, or crosses the boundary between x and y once. Therefore, the first stopping ensemble corresponds to allowing each branch to cross the boundary once. The second stopping ensemble corresponds to allowing each branch to cross twice, and so on. This naturally suggests using this sequence of ensembles to define a crossing sequence. Unfortunately, there's a problem. These ensembles are very messy objects which simply aren't suited for the kind of analysis one would like to perform in a crossing sequence-based lower bound argument. To avoid this problem, we replace each of these ensembles with the density operator that describes it, where, of course, many different ensembles are described by the same density operator, but they are all equivalent for our purposes. We then define the crossing sequence as the sequence of density operators corresponding to the ensembles we saw on the previous slide. To be precise, the first density operator describes the first starting ensemble, the second density operator describes the first stopping ensemble, which is the second starting ensemble, and so on. Next, I want to make one crucial definition related to crossing sequences, which is that of transfer operator. This corresponds to running M until it is finished computing on the prefix x. To be a bit more precise, these operators are maps from density operators to density operators, which convert any starting ensemble into its corresponding stopping ensemble. For example, the second element of the crossing sequence is the result of applying this operator to the first element. Of course, one also can define an analogous notion for a suffix y. Now, there are just two important observations I want to make about transfer operators. The first is that they describe the behavior of the machine on just a piece of the input, a prefix or suffix, and the second is that all of these operators are quantum channels, which plays an important role in the analysis. I conclude by sketching my lower bound argument. We need a few definitions. Firstly, for language L, we say that a pair of strings, xx prime, is ln dissimilar if there's a suffix y, such that the strings xy and x prime y both have length at most n, and exactly one of these strings is in the language. The Dwork-Stockbeier non-regularity of L is given by this function d sub L, where d sub L of n is the maximum number of pairwise ln dissimilar strings. Now, suppose we have a 2q CFA, M, that recognizes L in time t of n. We establish a lower bound on the running time as follows. We prove that there's a pair of input prefixes, x and x prime, which are ln dissimilar, and the distance between their transfer operators is upper bounded by this particular expression involving the non-regularity of L. Let's consider the consequences of those two conditions. We run M on the input xy and x prime y for some suffix y, which is a witness of ln dissimilarity. By definition, exactly one of these inputs should be accepted by M, and M will have running time t of n on both of them. We then consider the transfer operators, where, as we just discussed, these correspond to running M until it is finished computing on one of the prefixes, x or x prime. If the distance between these transfer operators is small, then on any single visit to one of x or x prime, M will have to behave similarly. But then, if the running time is small, M can't possibly make too many visits to its prefix string, and so now M will have to behave similarly on xy and x prime y. In particular, M will have to accept these inputs with similar probability, which is impossible because exactly one of these strings is in the language. Therefore, the running time must be large. Thank you for listening.